All right, in this video we're going to take a look at properties of parallelograms. So we saw previously parallelograms are categorized or classified by having basically being created by two sets of parallel lines in a transversal scenario where this opposite side is parallel to that one and this opposite side is parallel to that one. And also those two sides are congruent. So this one is congruent to that, and this one is congruent to that. So that's some of our important properties. So let's kind of break them down and look at each of these thing by thing. So our properties of sides is that opposite sides are congruent. And opposite sides are parallel. So angles, we get our angle relationships from this whole kind of transversal scenario where we know that at each intersection we have basically this angle and this one are vertical, but then to go from corner to corner, this angle and this one are corresponding. So these two are equal to those two. Then we have a corresponding angle and a vertical angle here, and a corresponding and a vertical angle here. So we end up with all 8 of those angles being congruent. Now, some of those aren't that interesting because they're outside of our shape, right? Like this corner, none of those are inside of our shape. But the two that are right here are our non-consecutive angles. So let's talk about angles. We know that from transversal rules, our non-consecutive angles, which I'm here going to call opposite angles since there's only 4 of them, opposite angles are congruent because we basically can take a step of corresponding and then alternate interior. There's a number of ways we could get there, but we know those two are the same. Likewise, if we did the same with our remaining angles, we know these two, these two, these two, and these two are congruent. So again, we end up with our other two opposite corners being congruent as well. So our property for angles is that the opposite angles are always congruent in a parallelogram. So that would allow us to set up, some problems and solve it if we knew expressions for those corners. But also, since these two are different, those are consecutive interior angles. So we could say, and any pair are consecutive interior angles. So we could say consecutive angles, so any two that are back to back are supplementary, which means they add up to 180 degrees. So we have two properties with angles. We know that opposite corners are equal and consecutive corners are supplementary. We also know that the total, just like it is for any quadrilateral, is 360 degrees for interior angles. So we have two pairs of supplementary angles, 180 and 180. Total is 360. But we also learned that every quadrilateral, no matter how you draw it, has, as long as it's convex, has interior angles totaling 360. Okay, so that's properties of sides and angles, but there are a couple of other things, one other important thing we can do here. So I'm going to do my best to draw this one well, because I want it to be kind of accurate. That's not terrible. Okay, so what we're going to do in some of these shapes, or all of these shapes, is take a look at their diagonals as well. So we have the 4 sides of the shape, but let's look at what happens if we draw a diagonal between our non-consecutive corners, or our opposite corners. So we have 2 diagonals that we can draw within any quadrilateral, because there's only 2 ways to connect through the shape. So that one and that one. Now, what I want to look at is, think about this is parallel to this, and this is parallel to that. This green is terrible. Let's use purple. That's better. Okay, so we have these parallel relationships. So thinking about our double parallel lines, I have this angle and this angle are congruent because those are alternate interior angles. So similarly, I know that, let's use a different, I'll use the same color, that this one along the one parallel line is congruent to this one along the one parallel line. So, and I know that this side is congruent to that side. I guess I looked at the wrong one there. I should have looked at this one is congruent to that one. We'll make those 3 marks. So basically what I'm trying to show here is that I have this angle congruent to this one, this side congruent to that one, and this angle congruent to that one because of all my transversal rules. So that gives me ASA congruence between this triangle and this triangle. So why does that matter? Well, one, we know that we have 2 pairs of congruent triangles here. We have the 2 purple triangles right here and right here are congruent, and also the 2 brown triangles right here and right here are congruent, but they're not all congruent to each other, right? Because we don't have all the sides of the shape congruent. So this left side and this top side are different lengths. So we get 2 pairs of congruent triangles when we split it with the 2 diagonals. But since the triangles are congruent, we can use that CP-CTC, congruent parts of congruent triangles are congruent, and we can conclude that this and this are congruent because those match between the 2 purple triangles or between the 2 brown triangles. So since those are congruent, then what we see is we have split the diagonal exactly in half. And the same thing has happened to this one. These 2 are congruent as well. So our property that we get out of that with the diagonals, so diagonals, is that they bisect each other. So they're not equal in length. There's a longer diagonal and a shorter diagonal, but they both meet at each other's midpoint. So this spot where they cross is the midpoint of both diagonals. So if I had an expression about this half of this diagonal and this half of this diagonal, we could set those equal and we could solve something. However, if I had this one and this one, I don't have a relationship between those because those are not congruent. So these are our properties for parallelograms. Then we're going to look at an example of some problems where we can use these to solve. So notice that usually we're setting something to be equal here, either opposite sides, opposite angles. Sometimes we have supplementary with consecutive angles. And then with diagonals, we know that they're bisected, so that's kind of like a segment addition, midpoint kind of problem. So let's look at some questions. So the properties we just went over, that's a spot you can fill those in on your notes if you would like. So each quadrilateral is a parallelogram. Find the missing measures. So number 1, AB is 15, so we know that DC is 15. And I like to go through and just fill in stuff on the drawing before I even look at this list over here. BC is 8, so AD is 8. We know opposite corners are equal, so this is 68 degrees. And we know that the consecutive ones are supplementary, so that must be 112 degrees. And then this one must be as well. So we should have filled in everything now, so hopefully that's everything they've asked for. Let's see, AD we labeled as 8, BC is 15, measure of angle A is 112 degrees, measure of angle B is 68 degrees, and measure of angle C is 112 degrees. So that's pretty straightforward. Number 2 is a similar exercise, so I'll leave that one for you to do on your own. Number 3, we get into looking at the diagonals, though. So that's one that we want to pay attention to. So since this is a parallelogram, we know that the diagonals bisect each other. So this is equal and that's equal. That means this one is 7. It says RT equals 30. So they've labeled that off the drawing so as not to be ambiguous. But what that tells us is that each half of it must be 15 because this is the midpoint. So then UT we know is the same as RS, that's 27. ST is the same as RU, so that's 18. VS was the same as UV, so that's 7. And VT was half of 30, so that was 15. So that's an example of a problem using midpoints. So we know that using diagonals and the fact that they meet at their midpoint, so we can know that they bisect each other and get more information about what's going on inside the shape. Number 4 looks pretty similar. Let's see what the difference. So we have the diagonals and the angles here. So we know that this 21 is also over here, and this 71 is also over here. We know that that's the same as that, that's the same as that. Oh, I missed the given information here. FED, so the big angle here is 134. I was wondering how we could get these other half angles. So we need to subtract 134 minus 71, and we get 63 degrees remaining here. And then we can populate the rest of the angles around. So we know that this corner and this one are supplementary. So we know that since we used up 134 over here at corner E, we have, 46 degrees left for angle F, and 46 minus 21 gives us 25. All right, so I think that should be enough for you to do the rest of this page. And then we're going to look at one other thing for today, which is proving parallelograms using coordinates. So parallelograms need a couple of things to be true. We need both pairs of opposite sides are congruent. So if AB equals DC, so here I'm talking about the lengths, so I'm not putting segment notation or congruent. I could have said if AB segment is congruent to DC segment, that would be fine. But here I just put length instead. And AD is equal to BC, then it's a parallelogram. So when I have all those two pairs of equal sides, then these have to be parallel as well. So we said that parallelograms have both the sides are both congruent and parallel for opposite sides, but one of those things is actually enough to fully constrain it. So we could also instead prove that both sides are parallel. So if we prove that AB, here I do need to say segment AB, is parallel to segment DC, and I know that AD segment is parallel to BC, then it's a parallelogram. So I don't know what goes in the U's. I guess this would be distance formula. This would be slopes because we're finding out they're parallel. Or if we have one pair of opposite sides is congruent and parallel. So if we have AB is both equal to DC and segment AB is parallel to segment DC, then that's enough information, and we would need to use both of those tools in order to figure that out. So this says determine whether it's a parallelogram using the distance formula, meaning they want us to, I'm going to just use this picture, ABCD. So they want us to see is AB equal to CD. So my distance from A to B is 8, 2. So that means 64 plus 4, that's the square root of 68. I could simplify that, but it really doesn't matter because I'm looking for CD to also be that same number. So I don't get any added value by simplifying it because then I just have to simplify this one as well. In fact, I probably didn't even need to do the distance formula. I could just say from C to D is 8, and from the y difference is 2. So then, yeah, this one was a difference of 8 and 2, and a difference of 8 and 2, meaning that they are the same length. They're both the square root of 68. So I know that AB is congruent to CD. But that's not enough. I need to either prove that they're parallel, which I would do with their slopes, or I could find out if BC and AD are congruent. Since it specifically says distance formula, we'll go that way. So from B to C, I add 8 in the x direction, and I subtract 10 in the y direction, which is, as far as distance, I don't care if I'm adding or subtracting. So the distance is 8 in the x, 10 in the y. And then from A to D, the distance is -7 to 1, that's 8. And the difference in y from 4 to -6 is also 10. So yes, this is a parallelogram because I've shown that AB is congruent to CD, and BC was congruent to AD. So that's kind of shortcutting and not doing the full distance formula, but you really don't need to, right? Because distance formula, just like slope formula, is just talking about change in x and change in y. So all I really need to do is find change in x and change in y, and if those are the same, then I'm done, basically. So let's do that one more time here. From -4 to 6, my change in x is 10. And from 2 to 4, my change in y is 2. Then for RS, my change in x is 9, and my change in y is 1. Well, those aren't congruent, and if they're not congruent, there's no way that this can be a parallelogram. So I don't even need to continue and check the other sides. As long as one pair of opposite sides, well, okay, hold on. They didn't give us the drawing, so let me just double check. So this is PQ. This was RS. Maybe, no, those have to be opposite sides because they have the different letters. PQ has to be opposite RS. Yeah, okay, we're done. I was going to say maybe I didn't know how the shape was drawn, but if I think about if this is P and Q, then it doesn't matter which one of these is R and S, it's still opposite of PQ. Right? I could label it RS or I could label it as RS, it doesn't matter. There are different lengths, so we're good. Okay. So that's an example of problems on proving parallelograms. Remember, you can also use slopes. Since I didn't put one on this page, just as an extra thing, I'll go through, let's look at the first one again. And instead of proving that the second one, so we had, we concluded from this part that AB was congruent to CD. Now, instead of proving like we did that AD is congruent to BC, let's prove that AB is parallel to CD to see how we could use this third method here. So our slope of AB is 4 minus 2 over -7 minus 1. So that's 2 over -8 is -1/4. That's our slope of AB. Our slope of CD is -6 minus -8, that's 2, over 1 minus 9, that's -8. So again, simplifying just means I have to simplify twice, so I could have just left it as the unsimplified fraction. But this shows that these two have the same slope. So now we have AB is parallel to CD, and we've used method 3 in order to show that this opposite side is both congruent and parallel. So yeah, there's some more practice on all of these within the booklet, so feel free to work on those and make sure you really got it down. But that covers all of the things we can do with parallelograms.